I'm Rohit Kumar Singh, and this is the seventh live session for the course Statistical Mechanics. I'm the teaching assistant for this course, and the course is being taught by Professor Dipanjan Chakravarti from ISER Mohali. So, in today's session, we will continue our discussion and problem practice. So last week we learned about the canonical ensemble and we solved some problems based on that. So so this week we will further generalize our discussion and we will consider another type of ensemble which is called a grand canonical ensemble. But before going to that topic, I would like to discuss a bit about the canonical ensemble. There is one concept left that I want to discuss, which is very helpful in solving problems of classical systems. So, for example, if you have classical ideal gas or relativistic gas, then and then to find the partition function for that for those kind of system, we'll have to consider the you know the density function which we discussed last time, the rho of the phase space, and so we know that so this density function, which is represented by rho, it's a measure of probability of finding a representative point. So which representative point on a phase space constitute a microstate. So probability of finding a representative point in the vicinity or small volume vicinity of the phase space point q given by qp, and this and we know that this probability in turn depends on the so this is basically the probability of finding a probability of a system with some energy E, right? And we studied that kind of probability, it is given by the exponential of this quantity, right? This we studied last time, and this is so this density function is also given by the same, it is proportional to the same quantity where h is Hamiltonian. Okay, and so then basically we can take this and so if you want to find the expectation value of some quantity f, then we have the recipe to do that. So we just using this expression where this dw is the phase space volume. Okay, so 3n coordinates of position and then 3n coordinates of momentum. Okay, and this quantity here is what we is what corresponds to, you know, the partition function, right? But we cannot directly write this as uh, qn. Okay, so qn is not directly this. Obviously qn is proportional to this, because this uh, we we need to know the, you know, number of distinct quantum distinct states of the system, right? And we know that the d omega dw value, so if we have dw volume in phase space, it corresponds to dw divided by n factorial and h to the power 3n distinct states of the system. Now this n factorial is coming because uh, if all the you know, all the uh, particles of the system are indistinguishable, identical and indistinguishable, and this h to the power 3n is the, you know, the smallest phase space volume, right? And so basically this cancel out the, you know, dimensions of volume, and so what remains is the distinct states of the system that is there in this dw value, dw volume. Okay, so finally our partition function in this case is this quantity. Okay, so it's an integral over the phase space volume. Now just notice how it is different from when we have the, you know, discrete state. So then our partition function was given by this quantity, right? Yeah, the sum is over all the different energy states possible. So this is another way of writing a partition function in terms of phase space volume. So this is very helpful while solving some problems of classical systems. Okay. Okay, then yeah, you will see how this formula will be useful in further in the problems while we'll solve the problems. So this is for classical systems. Okay, now the topic for today is the grand canonical ensemble. So I'll just quickly recap the concepts of grand canonical ensemble. So a grand canonical ensemble uh, is just another type of an ensemble, and it's a generalization of uh, the other two ensemble that we studied, the microcanonical and canonical. So in canonical ensemble, what we did was we allowed the exchange of energy, okay, and we fixed the number of particles, but that is also not very ideal, right? I mean, it is very difficult to fix the number of particles inside the system. Particles can move out or move in to the system, or get created and destroyed in the system. So so suppose, I mean, so for a simple example is, if you have a relativistic system, relativistic gas, or some kind of plasma or nuclear fluid or something, so their canonical ensemble cannot be applied, because their mass can, their particles can create out of nowhere and get annihilated, and all sorts of quantum phenomena can happen. So those kind of systems, to study those kind of systems, we need this grand canonical ensemble. So here uh, we allow the exchange of both energy and particles. So a grand canonical ensemble, it consists of a system, say system A, and as usual a large number of mental copies. So ensemble is nothing but just the copies of the system, mental copies of the system, having different microstates, all possible microstates. Large number of mental copies, carrying both, I mean, having both exchange of energy and particles. So so then again the question remains the same, like we had in the canonical ensemble case, like what is the probability that any act. So the question is, what is then the probability that at any time t, if you measure if you go and measure such a system, it is it has energy, some energy E and some number of particles N. So a system in ensemble has energy ER, suppose ER, and particles in NS, or we can write ES or NR. They are just dummy variables, so nothing to worry. S and R are dummy variables. So and this probability is given by, again, exponential of these two quantities, okay, where alpha and beta are two constants. So in this case, alpha is minus mu by kt and beta is the same constant from canonical ensemble, which is 1 by 1 over kt, and here mu is the our chemical potential from thermodynamics, okay. And so similarly, after normalization, we can write this probability like this. So sum over all the states, sum over states is what we call our partition function. So this is our grand canonical partition function. It is given by the symbol xi. So it is grand canonical partition function, or grand partition function also we can call it. So this is the probability that at any time t, system A is found to be in a state with energy Es and with particles Nr, okay. And then similarly you can have you can calculate various averages, like average number of particles, average number of average energy of the system, uh, like we did in the case of canonical ensemble. So yeah, for example, if you want to calculate the average number of particles, so what you can do is you can just sum over nr multiplied by this quantity divided by the partition function. Which can be written in very elegant form. So you can check that these two quantities are same, right? And this is our grand canonical partition function. So ln of log of grand canonical function, right? And similarly, you can write the expression of average average energy, which will be derivative of this log of grand canonical partition function with respect to beta. Okay, so once you have the partition function, you can calculate the average number of particles, average energy, and also you can calculate other thermodynamic quantities like entropy and pressure and various other things. So how to do that? So yeah, so like in canonical ensemble, we defined the Helmholtz free energy, right? We defined Helmholtz free energy as this, and then using the first law of thermodynamics, we calculated S, P, V, and other all the thermodynamic quantities. Similarly, here we can define another kind of potential, which is called grand potential, given by phi, and this is similar to Helmholtz free energy. There is an extra term which is mu n. Okay, and then if you take a small change in this function, so that you have small changes in all the other quantities on the right hand side, mu dn minus nd mu, and then you can put back the first law of thermodynamics. So du is equal to tds minus pdv plus mu dn, and then minus tds minus std minus mu dn minus nd mu. So this cancels out, this and this cancels, this cancels out. Yeah. This cancels out, and we are left with minus sdt minus pdv minus nd mu. Okay, and so we can write entropy as derivatives of this phi with respect to the quantities, thermodynamic quantities. And finally pressure as right. And also like Helmholtz free energy was related to the canonical partition function like this, right? If you remember. Similarly, the grand canonical partition, so the this grand potential is related to partition function, grand partition function, by this expression. Okay, this is I mean, we can derive this similarly as we derived this one, but this has been done in the lecture, so you can go and check. And so if you now you see, if you have the partition function, basically you can calculate the grand potential, and then you can calculate everything. You can calculate average energy, number of particles, entropy, pressure, whatever you want to calculate about a system, right? So this is very helpful. And yeah, you can so coming back to the partition function, which is given by this. Right. So so uh, I mean, this is basically a double sum, right? It is a sum over R and then sum over S. Sum over R is this thing, and sum over S is the energy, right? And if you define a thing called small z by e to the power minus alpha, so this is called fugacity. Okay, if you define this quantity, then your partition function can be simply given as z to the power nr and this so the double sum is there, and it can be simply written like this. And now you notice this is just the canonical partition function, right? So grand canonical partition function can be written in terms of the canonical partition function. Okay, and this is also, this we can also use in problems. uh, yeah. Then there is I mean, so you can calculate the average number of particles using this formula, but there is another another nice way to calculate this. So suppose you don't have, I mean, suppose you don't want to take the, so taking the derivative with respect to alpha can be complicated, but since you have written the grand canonical partition function in as a I mean in terms of this fugacity, so you can calculate the average number of particles. uh, I mean, there is another expression which is given by this. So instead of alpha, because alpha and z are related like this, so you can derive this thing. So this is another way of calculating the average number of particles. This is very easy to derive. So okay, let me derive it for you. So to derive this, So to derive this, what you can do is you can just differentiate this grand canonical. So take log of this grand canonical function and differentiate it with respect to z, right? So this is what we are doing. So what you will get, you will get uh, 1 over grand canonical function and del of this by del z, right? Now from here, uh, derivative of grand partition function with respect to fugacity explicitly can be given by this, sorry. So I'm just I'm just taking derivative of this with respect to z. So rs, so nr z nr minus 1, and this qnr is remains remain like it because it is constant, right? It does not depend on n. So I mean it is a constant function of fugacity also. Now if you multiply on the both side by fugacity, so multiplying by z on both sides, so this will become this, right? And now you notice what is this. So yeah, so, so simply this is just, if you are taking number average, this is just this should be sorry, yeah. This is true, right? From here you can see it is the same thing, right? And so uh, nr is equal to n times the partition function, right? And so z del of z is equal to average number of particles times partition function. And you can take this down here, so this will be del of del z ln z, right? So this is what this expression is. Okay, so this is just a nice way to calculate the average number of particles. This is very helpful in solving some problems. Okay, what else? Yeah, I think that's it for the recap. So let's now go to solve some problems, okay, based on these. So okay, let's go to the first problem for today. Okay, no, so this is a uh, problem with classical systems. Okay, so the problem reads, consider a classical ultra relativistic gas of particles given by Hamiltonian. This is the Hamiltonian, where C is a constant, and this is, I mean, this gas is contained inside a container of volume V. Now, since this is a ultra relativistic gas, so particles can create or destroy, right? Or and it is given that it is in contact with a reservoir of heat and particles, so it can exchange energy and particles. So right away you know that you need to use the grand canonical partition function for this problem. And the question asked is the expression for grand canonical partition function and the grand thermodynamic potential. Okay, so we just I mean, we just saw the formula of these two quantities, so we can just simply apply them here. Okay, so Hamiltonian is given. Okay, so this pi is the four momenta of the sorry, the momentum, basically the momentum vector, three momentum vector of the particles, right? And I goes from 1 to all the number of I mean total number of particles. So I is equal to sorry, I is equal to 1 to n, right? And so and we know that for a classical system, uh, for a classical system, uh, the partition function is given by, so this expression, right, that we calculate. So this is a canonical partition function, not the grand canonical. But we know that if you find find our canonical partition function, we can use this formula. Sorry, this formula to calculate the uh, grand canonical partition function, right? So let's first calculate the canonical partition function for this. And the canonical partition function is given by sorry, let's write it. Qn is given by 1 by n factorial h to the power 3n, right? And yeah, and we also know that Yeah, I mean, it is fine. We can calculate, or yeah, we know that Qn is just Q1 Qn to the power n, right, divided by n factorial. So we can easily calculate Q1. So partition function for a single particle, which will be given by 1 by h cube, right? So from here you can calculate Qn, which is equal to n factorial Qn right. And so Q1 will be equal to, so this n factorial cancels out with the n factorial in the denominator, and you get, sorry, you get this, right? And then you can take, you can take 1 by nth root of this, so it will be this, and then dw 1 over n. Okay. Which is so actually no, it doesn't work like this in this case. I mean, you can derive, you can, through this also you can, you will go to the same result, but we have this expression, right? And where the q1 is given by, it will be given by, so for one particle the Hamiltonian will be just, Cp. So Cp, and then dq q and dq p, right? And so the integral over coordinates will give you the total volume of the container, right? So v, and so we are left with only the integral over p, because this does not depend on, position. So that's why we were able to integrate the position coordinate to the volume. But to integrate this, we will have to consider, a spherical coordinate system. So we can write this further. So in a spherical coordinate systems, this dqp, the volume element, is given by 4 pi 4 pi dp p square, right? So here we have p square dp. Yeah, and this is a very famous integral, right? So to calculate this integral, uh, what you can do is you can use the substitution method, or use integral by parts. uh, so what you can do is you can put u is equal to p square, and then du will be your uh, or you can yeah sorry, yeah, u equal to p square, and then du will be what, 2p dp, right? And also you can write, so v so you can also write v equal to um, minus 1 over beta c e to the power minus beta c p, right? So that your dv will be equal to e to the power minus beta c p dp, right? So together with u and v, you can have this integral dp, sorry, p square dp, which is this integral. It can be given by so I mean, so first let's do the integral by parts for this. So you will be left with minus, so first you do this integral, and then you do in the second step you do the differentiation. So the normal integral by parts you do, you have p square as it is, e to the power minus beta cp, okay, and then you have differentiating this, 2 factor will come outside, beta c will come from the integration, and you are left with p e to the power minus beta c p dp. So this is the first integration by parts. Then you again have to do the integration by parts for this, and okay, so this is okay, so let's do that. So you have this thing, by the way, this goes from 0 to infinity, right? And as you can see that this is uh, this quantity is 0, because at infinity this is 0, and at 0 this p square is 0. So this whole quantity is 0 for the limit. Now let's go to the second integral by parts. So here you have uh, so okay, so let's take this outside bracket, and then you have minus 1 by beta c p e to the power minus beta c p. Again, for 0 to infinity this goes to 0, right? And then you have plus 1 by beta c square because you already have 1 beta c here, and you are taking another uh, integration, and then you will have minus beta c p dp, and this is now very easy to integrate from 0 to infinity. uh, so you are left with only 2 by beta c, and then you have, so if you integrate this you will have 1 over beta c. Yeah. Yeah, 1 over beta c, I think. No, sorry, there should be only one beta c here. Yeah, this is just one beta c here. Okay, so now you have beta c square, and you have minus beta c p going from 0 to infinity. Now at infinity this quantity is 0, but at 0 this is 1. So finally you have 2 over beta c cube, right, and 1 minus 0, so this is negative. Yeah, this is negative, should not be negative. Sorry, this will be negative. Sorry, yeah, this will be negative because we are doing integral, so this will be finally positive. So what you have now finally is this thing is given by this. So now you have here, what you have here is 2v divided by h cube beta cube c cube. Okay, this is the q1. Oh sorry, and you have here 4 pi also, so it will be 8 pi finally. Yeah, so it's a little bit complicated, but these kind of integration will come very often. So yeah, you don't need to do. Also, you can do this with substitution, but integral by integration by parts works very well here. Okay. So yeah, now you have the q1, then you can calculate the qn, and then so finally your qn will be qn will be given by q1 to the power n divided by n factorial, right? So just simply, so I'll just write the total expression. So it will be so the qn will be yeah, or qn will be just qn to the power n by n factorial, and then your grand partition function will be z to the power n qn, right, which is z to the power n by n factorial q1 to the power n. Now this is this you can write, I mean this is just series which is an expansion of exponential of jq1. You can check, you know that exponential of x is given by sum over x to the power n over n factorial, right? So here x is simply jq1, right? And sorry, I ran out of space. Let me take some space from the next problem. So finally, I mean you can write it as exponential of 8 pi v e to the power beta mu, the fugacity, and divided by h bc whole cube, right? Because z is equal to e to the power minus alpha, which is to the power beta mu. Okay, and then the grand potential function, as you know, is just kt ln of this, which will be 8 pi v e to the power beta mu. So ln will cancel with exponential, and you have another b here, which beta cq. Okay, so correct answer is which one is correct answer? Yeah, this one. Both are same. No, this one is correct answer. Yeah. Okay. Now now you have the, you have everything, right? Sorry, this is phi. You have grand potential partition function and grand potential. Now you can calculate everything. So pressure, as we saw earlier, it is given by just the derivative of volume of this function of this grand potential from here, this, right? So you can calculate entropy, pressure, whatever you want to calculate, all the thermodynamic quantities. So if you take the derivative with respect to volume, you simply remain with 8 pi e to the power beta mu divided by beta h beta c to the power q. So see how easy it is to calculate the pressure for this kind of system if you have the grand potential function. Okay, so let's now move to the next problem. Here the grand partition function is given, and we want to calculate the zeros of this polynomial. So this is uh, not a very, I mean, this is not related very much to statistics. It's just a mathematical problem. Uh, so zeros occur when either this is 0 or the second term is 0, right? Now this one will give you z equal to -1, and this one will give you z alpha v equal to -1. Now solving for this, z is equal to, so this will be 0, I mean this will be -1 at many instances given by this periodic function where n is equal to 0 plus -1 plus -2, right? So we are choosing this to be a complex function, okay, because the question asks the answer in a complex j plane, okay. So j can take complex values, so that's why uh, we are choosing it like this. So then the correct answer is this. I mean, so you know that in a complex plane, this is the real axis and this is the imaginary axis, and -1 -1 can come, I mean any complex so this quantity can be -1 at various instances, so this is a -1, but there can be other points in the complex plane whose magnitude can be -1. So all those are considered in this expression. Okay, so that is all I have for today. So I hope you understood some of the things about grand canonical partition function and grand canonical ensemble, and I hope it will help you to solve the problems in the tutorial assignment. So okay, so this is all. Let's close this session today and meet next Saturday. Okay, thank you. Bye.